Hi, welcome to your 9-1/9-2 flip video. 9-1 is about solving inequalities using addition or subtraction, and 9-2 is about solving inequalities using multiplication or division. So it makes sense to kind of squish these two into one flip video because they're very similar. We're just changing the operation we're looking at. So to backtrack a little, what is an inequality? Well, an inequality, if you break down the word, let's break down equality, equal. So it has something to do with equal, things being equal or not. In is a prefix that means not. So an inequality is a mathematical sentence that does not use an equal sign. So some examples of these would be less than, greater than, less than or equal to, greater than or equal to, or not equal to. So we have these 5 different symbols that replace the equal sign in a mathematical sentence, which changes the meaning of that sentence. So let's break each one down. So an example of a less than statement would be x is less than 2. So what does that look like on a number line? What are some possible answers? Well, if you have a number line, I'll make a very simple one, and you plot x is 2, you do that, x is less than 2. You do that by first identifying the number, so it's 2, so right there, and I'm going to represent it with an open circle because it's less than. X cannot be equal to 2. It needs to be less than 2. So what's the biggest number x could be? 1.9999999 forever. But it can never be 2 because x needs to be less than 2. So we represent that by shading in the area on the number line that represents all the numbers less than 2, which means go to the left. Because when you go to the left on the number line, numbers get smaller. And if you go to the right on the number line, numbers get bigger. Values on the right are larger than values on the left. That's why it's a number line. So x less than 2 is an open circle at 2 and a shading in everything less than that on that number line. So possible solutions, any number less than 2. It cannot be equal to 2. It has to be less than 2, but it can be any number. It could be negative 1,000. It could be 1.5. It could be 1.9, 1.99, 1.999999999. Any number less than 2. All right, let's work on the greater than. So x greater than 1. So again, here's a number line. And identify the 1, because it's a comparison in reference to 1. And now open circle, because it's greater than, it does not include 1. And then everything greater than 1 would be everything to the right, and we represent that with that shading in it. All right, and then solutions, again, would be any number greater than 1, not including 1. All right, less than or equal to, so x is less than or equal to 10, would be an example. And you do your number line, and then identify 10. And now we're going to use a closed circle, because 10 can now be included. X can be 10, but x can't be greater than any number more than 10. So x could be 10, but x can't be 10.000001. That would not work. So we use a closed circle to represent that 10 is included as a possibility. And then less than means go to the left, so we shade in everything to the left. And that is your number line that represents x is less than 10. Possible solutions, any number 10 or less. 10 is included in this scenario. All right, that same logic applies to greater than or equal to. So let's look at x greater than or equal to negative 20. Make your number line. So we identify negative 20, and then greater than or equal to means negative 20 is included as a possibility. So we use a closed circle, and then greater than means shade to the right, and we go ahead and do that. And then solutions, negative 20 or anything bigger than negative 20. Negative 10, 5, a million, 2 million, any of those. All right, the last one we have is not equal to, and the example would be x not equal to 5. So if you look at the number line, identify the 5, and now x can be any number except for 5. X is not equal to 5. So let's look at the right side of 5. Anything that's not 5 to the right of 5 would be everything greater than 5. And then anything to the left of 5 would also work. So what's the only number x can't be? X just can't be 5. And we represent that hole, right, between the right side being shaded in and the left side being shaded in with an open circle. So the number line to show x is not equal to 5 is a shaded in number line everywhere except for the 5, which is a hole in that shading, and we represent that with a open circle because it's not included. So solutions, literally any number except for 5. All right. I want to look at one little example. X is less than or equal to 7. So when I give you an equation, something with an equal sign, let's say x is equal to 7, none of you would argue that that is different than 7 is equal to x, right? You can flip the sides of an equal sign because an equal sign means the left is equal to the right, and therefore the right is equal to the left. But when we do that with inequalities, we need to take into account that it's not they're not equal. They are different values, and it's a representation. An inequality is a representation of the relationship. So let's just flip the location of the x and the 7. Let's put the 7 there and the x there. In our original one, x is less than or equal to 7. X needs to be smaller than 7. So if I flip the order and say 7, what's 7's relationship to x? Well, 7 has to be greater than or equal to x. So if you flip the inequality, you need to flip the symbol because the relationship needs to stay constant, right? 7 needs to be bigger than x. And on the flip side of that coin, x needs to be less than 7. All right, we can do the same thing with all of these, but the inequality, the not equal to, is a little tricky. Don't get mixed up here. It doesn't flip from being not equal to being equal to, right? If you have x not equal to 5, 5 is not equal to x. It doesn't change the meaning of the relationship, it just changes the order in that case. For all the other inequalities, you change the direction that they're facing, okay? And that's it. Let's look at some practice problems. So when solving an inequality, and these are all one-step inequalities, you just pretend that inequality is an equal sign and then solve. So we have an addition, a subtraction, a multiplication, and division, and we'll look at some crazier examples in a second. So let's isolate x in that blue equation. How do you get, if that was an equal sign, x plus 5.1 is equal to 12.3. How would you get x by itself? Well, you'd subtract 5.1 from both sides, they'd cancel out, and you would get x is greater than 7.2. So you just pretend it's an equal sign, and we know it's not, but the rules for equations still apply. So now let's make a number line to represent this, and number lines generally, you can't go wrong with them. Ideally, your number line is a good representation of the data. So in this example, 7.2, x is greater than 7.2. So I wouldn't want 7.2 to be my number all the way on the right, because then that would show a lot of things x can't be, but very little of what x could be. So let's identify 7.2. It is it's a greater than, not greater than or equal to, so open circle, shade in everything to the right, and that's our number line that represents that. All right, so if you move to the green, how do you get y by itself? You're going to add 1/2 to both sides. Cancel out on the left. You get y is less than 5 3/4 plus 1/2. And I'm going to leave it like that right now because we're going to have to add the pieces. Let's go ahead and change 5 3/4 into an improper fraction. So 4 times 5 is 20 plus 3 is 23. So 23 over 4 plus 1/2. And now I'm going to have to change them to have common denominators. So I see 23 over 4 has a 4, and 1/2 can be scaled up to have a denominator of 4 pretty easily. You just multiply the numerator and the denominator by 2. So you get 23 over 4 plus 2 over 4. And now you can add those pieces of the numerators. You add the numerators, but you leave the denominators alone when you add or subtract. So y is less than 25 over 4, and we can change that into a mixed number. Y is less than 6 1/4. So if you make a number line, again, you want the number that you're looking at to be roughly in the middle. I wouldn't want 6 1/4 to be the number all the way on the left or all the way on the right, because that shows it's a very limited view in that case. So I put 6 1/4 is roughly in the middle. Let's identify it, and then it's a less than, not a less than or equal to, so a full open circle, and then less than mean go to the left, shade and everything. So that's your number line that works with that. 10.1 times x is greater than or equal to 111.1. You're going to divide both sides by 10.1. 10.1's cancel on the left, so you get x is greater than or equal to 11. So make your number line, identify 11. It's greater than or equal to, so we're going to do that circle, but we are going to go ahead and we are going to fill it in because 11 is an option for us. 11 could be an answer. And then we shade to the right because x is greater than 11, greater than or equal to 11. X divided by 9 is less than or equal to 15. Going to multiply both sides by 9. The 9's cancel. You get x is less than or equal to 135. Make a number line, 135 roughly in the middle. Identify 135. Closed in circle again because 135 is a possibility. And then everything to the left because x is less than 135. All right. Now, when you multiply or divide by a negative number, you must flip the inequality sign. And this is something we talked about. This is the only time where the rules for equations does not apply to inequalities because inequalities are a relationship. Equations, while also a relationship, equations kind of self-balance themselves. Inequalities, there's multiple answers for every inequality, right? If x is greater than 3, it could be 4, 5, 6, 7, any of those numbers. Equations, there's only one answer. So equations self-regulate themselves. Inequalities need a little help when dealing with multiplying or dividing negative numbers. So let's look at a very simple example. If you have 1 and 3, 1 is less than 3. No one's going to argue that 3 is less than 1. 1 is clearly less than 3. So if I take a number line, I plot out 1 and 3. Let's go ahead and make 1 blue and 3 red. So I'm going to make a blue dot at 1 and red dot at 3. Now, if I just look at that little scenario right there, the blue dot is on the left. 1 is less than 3, so 1 needs to be on the left of 3 on the number line. Now, let's multiply by a negative number. Let's multiply by, let's say, negative 2. 1 times negative 2 is negative 2, and 3 times negative 2 is negative 6. So I'm going to keep the colors for those products. I'm going to plot those products here. So 2 and negative 6. And now you'll see the blue dot is more to the right than the red dot. Negative 2 is greater than negative 6 because negative 2 is more to the right. So if I look at that scenario, the blue dot is now on the right. So what has happened is the relationship between the two dots has changed relative to each other. The blue used to be on the left, but now it's on the right. And we represent that change by flipping the symbol. So let's look at some examples. Negative 3 times x is greater than 12, and x divided by negative 2 is less than 20. How do you get x by itself? You divide each side by negative 3. So what I do, when I see I'm dividing or multiplying by negative 3, before I even cancel anything out, I flip that inequality so I don't forget to do it later. Now, once I have it flipped, I'll just pretend like it's an equal sign. Those negative 3's cancel out. You get x is less than negative 4. So you draw your number line, identify negative 4. Now it's a less than inequality, so open circle, and then everything to the left. All right? And you can check it. So let's say so you can check your inequalities by picking a number that makes it true. So the one that we solved, x is less than 4, we'll pick a number that's less than negative 4. So I pick negative 5. Negative 5 is less than negative 4. And then plug it into your original inequality. So negative 3x is greater than 12. So negative 3 times negative 5 is greater than 12. And then solve. Negative 3 times negative 5 is 15. 15 is greater than 12. That's a true statement. 15 is greater than 12. So I know I've gotten it right. All right, now let's look at the blue one. X divided by negative 2 is less than 20. I'm going to multiply both sides by negative 2 to undo that division by negative 2. And now I see I'm multiplying by a negative number, so I'm going to flip that symbol first. So it changes from a less than to a greater than. Those negative 2's cancel, and we are left with x is greater than negative 40, because 20 times negative 2 is negative 40. Make your number line. Identify negative 40. Now it's an open circle because it's not an or equal to. And then x is greater than, so we're going to shade in everything to the right. Now, these also work for less than or equal to and greater than or equal to. So, let's double check really quick. What's a number that's greater than negative 40? Let's pick negative 20, plug it back in. Negative 20 divided by negative 2 is 10. 10 is less than 20, so I know I got it right. All right, these also work for less than or equal to or greater than or equal to, so let's change those original equations. Let's make them or equal to. So fill in the circle, and that's the only change. Everything else stays exactly the same. Same thing for the blue one. All right, and that is it for 9-1 and 9-2, solving inequalities through addition, subtraction, multiplication, division. For all of them, you just pretend that it's an equal sign, except for when you are multiplying or dividing by a negative number. Has to be a negative number, and it has to be multiplication or division, and only in that one scenario do you flip the inequality. Let me know if you have any questions.